Okay, so now into data screening for regression, because it is different. It's not that different, so don't freak out. Since we were doing ANOVA before, and we were trying to actually screen Y generally, we had to do a fake regression. But now that we actually have Y and continuous X's, we want to screen the X's and the Y's. So since we're running a real regression this time, we do not have to make it fake. So before we had to have a random variable to make sure that the DV was appropriate. Now we don't need that random variable because we have real regression, so to speak. ANOVA is still regression, but we have to do something special to make it work. So we're going to get to do data screening with the real regression rather than the fake one, which basically means you don't have to create a random variable. It does mean you have to run the analysis before you do data screening and then run it again. So you kind of have to run the analysis twice. But we're going to walk all the way through that in the example today, just to make it clear what's going on. So you're still going to check missing and accuracy the exact same way. That doesn't change. Outliers are somewhat new and exciting, so there's a slightly different procedure. Multicollinearity is the same procedure with an asterisk because there's an easier way to do it. And then all of the other assumptions stay the same. It's just we don't have to run anything fake. It's all real. So let us do some alcohol examples today. So I have the CESD, which is a depression measure, a measure of meaning, on the audit, which is sort of a measure of alcohol abuse, and the DAST, which we don't actually use the DAST, we're just going to use the audit. So we're going to create a model where we're going to use meaning in life and alcohol use to predict the depression scores. And so we should get a negative correlation for meaning in life. As you have more meaning, you should have less depression. And if I had to predict alcohol scores, I would predict they would go up together, but we'll see what happens, since I already know what happens. Since this is multiple regression, this is from the book, so just kind of give you, how does it actually calculate the slopes? Because there's two slopes involved at once. So what it does is it takes the y-intercept for just the overall average of y, right, v sub 0, but then it creates a sort of 2D picture, right, with two of them, 3D with more, and it figures out, given your meaning score and given your alcohol score, here's your predicted value. How close is that to y? But you have two of those scores. So when we did the fitted values before, what we're doing is calculating the predicted score for each person. So here's my predicted score, here's your real score, and then that's where the residuals come from. So this is what it would kind of look like in a graph. You don't tend to make scatter plots for these because that is unreadable. If you had 4 variables, you can't graph it. There aren't really pictures for regression so much. There are pictures for like mediation and moderation, but we won't get to those. So let's try loading up the data. So it's an SPSS file, so I went back and loaded it as MIMISC. Just to practice that again. So what we've got is actually I have a bunch of variables, but the one I'm most interested in is pill total, CESD total, and audit total. So this actually was a project that got published a couple years ago. We were looking at meaning, alcoholism, and depression, and gender. And so for men and women, you get different sets of slopes depending on their alcohol use. So it's actually an interaction. So what I have on line 17 is I just dropped all the extra variables just to get rid of them. So now we've just got the 3 we're interested in. So when you have regression and you have a bunch of extra columns, just get rid of them at the beginning. It makes data screening much easier. So for a summary of that data set, I don't have any missing data because I didn't want to screw with it. So no mice today on an R. But I could look and make sure the min and the max were okay. So this is where I check for accuracy, and it's fine. And so what I want to do is I have to actually run the regression first to be able to get the rest of these scores. I don't actually have to run it to get Mahalanobis, right? That's separate, but I do for the next one down, and we're getting to what those are in a minute. So we're going to run that, and it's essentially the same format we've been doing. So that's why we spent all this time doing y is approximated by x plus x, because it's like the same all year. We're going to use that function. So we're going to put in y here, which is going to be CESD. That's really odd, because I can hear him moving. Plus audit plus pill. So back over here. So we're going to run that and call it model 1, or I should call this really temporary model, or like data screening model, whatever makes sense to you. And I don't want to look at any of the coefficients for this model, because this is where we're still doing data screening. So even though we have to run it, you don't want to look at it and be tempted to use those scores, because they may change here in a minute. All right. So then Mahalanobis. It's the exact same thing we've been doing. But we're going to save a column of data with the cutoff scores. Okay. So I'm going to change this just a little bit. Make this bigger. Okay, so here we are under Mahalanobis. So Mahal equals Mahalanobis. I've got my data set, so I've included all 3 columns. So that's actually going to screen both x's and y. It's going to pretend like it's just all one big data set and screen all 3. So this is screening both x and y. Okay. And then call means and covariance. The cutoff score is still q chi-square, so 999, or 1 minus alpha. And then the degrees of freedom is for the number of columns, so it would be 3. But then this next line is new. So I call this bad Mahalanobis. So these are the people who are over the cutoff score. Note that that sign is a different direction than what we've been doing. So I'm finding everybody whose Mahalanobis score is over the cutoff score. And then I did as dot numeric. What does that do? So I'm going to run that. Okay. What that does is it creates me a column of saved data. So I have it saved over here. That is, there should be 1. Here's the 1. Right. If they are an outlier or not. I might want to put a note on it that says don't touch.
We'll let them find out the surprise themselves.
Yeah, he was screaming from the hallway. I would tell you, seriously, put a note on it. There you go.
That's just too distracting.
All right, so what does this column do? It's a list of the people whose scores are above the cutoff score. And this is going somewhere, I promise. Okay. The next thing we're going to do is talk about leverage. So this is totally new. So before, get it back. Thanks. Leverage and then the next one, cooks, weren't too useful because we were dealing with means only. Now, since we're looking at slopes, we're going to use 2 new outlier rules. So we've got Mahalanobis plus what's called leverage. So let's say everybody is in this nice pretty line and your data is perfect. Leverage is a person who influences the slope. So someone who's way up here or way down here is going to influence the slope more than somebody who's here or even here. So you can think about leverage like a lever. And like you're changing your car tire, you have to get leverage, right? So they're changing the slope by pulling it up or pulling it down. So this point does not have leverage because it's within the range of the slope. So leverage is a measure of how much they're changing B. The cutoff score for leverage is 2k plus 2 divided by n. Remember, k is a number of predictors. So in this case, it's 2. So 2 times 2 is 4, plus 2 is 6 divided by n. And the way we can get them in R is called hat values. They have a little, the symbol for them has a hat. I don't know why they're called hat values. But we're going to run the hat values code here on the model. So that's why we had to run the regression first. It's because this is like considering everyone who has the largest leverage. So we're going to save those. So I did k out here just to make it clear. So I made it 2. So I wouldn't have to remember to change it here later. Right? I change it here and it affects both of these 2 that we're talking about. So I got 2 IVs. Run the hat values just to get them saved. Okay. So it's a bunch of seemingly very tiny numbers. Okay. So remember, this is how much influence they have on the slope. So how much is the slope going to change if included? Okay. So it looks at the slope without them and the slope with them, and then subtracts the 2. Okay. My cut leverage here is the cutoff score. Again, I try to make these as flexible as possible. So I only have to change k on line 37 and the data set name. So I don't have to change n there. It's just the number of rows. So let's see what that cutoff score is. It's 0.022. So anybody who's over that score has an undue influence on the slope. And then we're going to do the same thing we did here on bad Mahalanobis. So people who are bad on the leverage score. And you'll see that there will always be more of those. It's easy to have an influence on the slope. Okay, so there are a lot more ones here. What I like to ask on the homework, how many of those did you have? So I made a little table, 16. Okay. 0 means their score is less than the leverage. 1 means their score is more than the leverage. The cool thing is the way that you have to do this in SPSS sucks heartily. This is much easier. So it's a couple of lines of code, but it's just a way to keep track of who's bad on which one. Okay, so for Mahalanobis we have 1. For leverage we have 16. The next one we're going to do is Cook's. It's called influence. Influence is a measure of how much a single person has an effect on the entire model. So like more about F and R squared. It's often described as both leverage and discrepancy. So discrepancy is when we have it done. So discrepancy happens when there's a break in the data. So you have people who are all here, and you have a big space, and then somebody way out here. So this person would be discrepant, but no leverage. Somebody whose score is here would be both. So they're far away from this part of the data, so everybody else's scores on Y are here. So there's a big gap here, and they would have a very bad influence on the slope, so they would pull the slope up because they're higher than everybody else. So Cook's is the measure of how close they are to X and Y mean, and how much leverage they have. It also has a different cutoff score. It's 4 over degrees of freedom, so n minus k minus 1. And it has a nice name, Cooks.distance. So how far away are they from everybody else? So we have to run that on the model that we saved. So model 1, that's why we had to run the regression first without looking at it. Cook's is 4 divided by n minus k minus 1, same k as earlier. The bad Cook's, how many people are above the Cook's score. And then a table, so I got 17 bad Cook's. So we've created 3 new outlier columns. And we want to know who should we get rid of. Because before, all we did was look at the mean of the means. So Mahalanobis, remember, is the center of the mean of the means. And since we were using means as our model, that made sense. But now that we have slopes as the model, we can still look at the means, because that's where the intercept comes in, right? Because the intercept is the mean. But we also have to consider how much they're changing the slope, because the outlier is even a bigger problem with slopes. So we have 2 extra things to run. There are tons of them. There's fits data, defits data, there's studentized residuals, standardized residuals, just straight z-scores, studentized deleted, there's a bunch. These are the most popular ones. So these are the ones I use when I do regression research. So what do I want to do with all those numbers? We've already screened them. Let's add them all together. And then take out the bad people. So I added them all up, total out. So that's their Mahalanobis plus their leverage plus their cooks. So out of all of that, how many people are problems on those? I got 240 participants that have no issues, 21 participants with 1 problem, 5 people with 2 problems, and 1 person who's bad on all 3. So in the end, when I ask you how many total outliers did you have, the answer here is 6. So everybody who's got 2 out of 3 problems, we're going to get rid of. So if they're problematic on 1, okay. If they're problematic on 2, you're out. So it's kind of like baseball, only you only get 2 strikes. So I'm going to create myself a no-out data set where I subset the master data set that I was just working with, where their total outlier is less than 2. And so that got rid of 6 people who had 2 or more problems. So it's kind of like 12 lines of code, but it will help you keep track of each one separately. So I don't think I actually wrote that it's 2 out of 3. So be sure you have written down on this that it's 2 out of 3. That's what you want to get rid of. Questions? No, not yet. Okay. So for multicollinearity, I'm going to suggest you not screen this the normal way, because then you're going to probably be like, oh, well, X and Y are too correlated, and you want X and Y to be correlated. Like, that's the point of regression. And so to not even have that problem, we're going to screen it through the regression analysis. There's a way to get it to give you the correlations. Okay. So you don't want X to be highly correlated with other X's, because you'll lose power. Okay. So you're losing degrees of freedom for every X you have. And if you have a bunch that are highly correlated, it may not run 1, but it also is a waste of time. Sometimes what will happen is called suppression, where if you have 2 X's that are very correlated, one of them will get all the variance and the other one won't get any. So it'll look like one of them is super important and the other one doesn't matter because the other one kind of won the race. Right, so we got 2nd place. And that's pretty common if your variables are correlated at 0.6 or higher. Okay, they might cancel each other out. If they're correlated at 0.7, that means they share 50% of their variance. And then if you're trying to compare their variance to a DV, you're basically like, it's all too correlated. And in super fun times, what sometimes will happen is none of the variables will be significant because they've all kind of canceled each other out, but the overall model is significant. It's like the worst thing to have happen because you just start, you're like, what the hell? R squared is 0.5, but none of the variables are important. And that's when you should try taking out the ones that are super correlated as suppression. All right. So how do I get that? We're going to rerun that model now on this 2nd data set. So I copied the line from above, and I'm running it without the outliers. So this is the no outliers model. Okay. And then I left you a note on why you got to rerun it. Now, what I can do is tell it to give me a summary correlation equals true. And what that does is it gives me the actual regression output, which we're not going to cover quite yet. But it gives me this correlation table at the bottom. So let's see here. Oh, I didn't cut and paste it. Sorry. What you want to do is look at the correlation between the variables, but not the intercept. So ignore this intercept thing. That's how much X is correlated with the Y mean. Like, I don't care. Really, I want to look here. And the meeting and life scores and the alcohol scores are only correlated at 0.15. So they're not, it's not a problem. Okay. So multicollinearity is still 0.9 is the rule, but at 0.6 and 7 is when you're going to start to have trouble with a regression where they might cancel each other out because it's just too high. It's not a multicollinearity problem, it's just generally like, oh, which one is going to win? It's more of a suppression issue. All right. So that's kind of like the easy way to not look at the correlation between x and y and tell me that it's multicollinear because x and y are correlated, because you want x and y to be correlated. You can also do it the old way with the core function. All right, last thing we're going to cover is the same set of rules that we did with ANOVA, linearity, normality, and stuff. So what I'm going to do is I don't have to run a fake regression. Check it out. So it says assumptions. I'm going to get my standardized residuals. Okay, these are actually the studentized residuals, but I ran it both ways. It's the same. Okay. And my fitted values, but no fake. Right? We have a regression. We don't need to run a fake one. And then it's the same code we've been using. So QQ norm, my AB line. Whoa, that looks crazy. Why is it rectangular? Let's try it more like this. All right, so that's not linear. Right. That's kind of curvilinear. So I should probably look at this in a power function way. But we're not, because this is an example, but that's not a good graph. I don't know why my graph looks crazy. There we go. Let's look at the standardized residuals. That's pretty normal. You'll always have the one dude way in space, but most of the data is centered over 0, 1, 1. Pretty normal. And then homogeneity and homoscedasticity. More on the homoscedasticity now, because I don't really have groups. And yeah, that's not good either. So homogeneity-wise, it's bad, because most of the data is between 2 and 2, but we still got 3 and 4, and there are more dots down here. So it's either homogeneity, this is not so awesome. This way it's fine. Homoscedasticity-wise, which is more important, it's a pretty even spread. I might draw a submarine, but it's pretty even. Y'all have gotten good on the pictures, but it's pretty even. So what do I do if the assumptions are bad, though? So on this data set, I should try non-parametric regression, which is a different function. There's a good one called RFIT. So nonlinear regression. Normality is still pretty robust, so add more people if you just don't have that many. And then homogeneity or homoscedasticity problems, excuse me, bootstrapping. The book talks about bootstrapping, but we're not going to cover it. Bootstrapping is when you run lots of little samples. So I take my data set and I make lots of data sets from it and then run it multiple times to see if the values are fairly consistent, which will sometimes have data sets that are homoscedastic and sometimes have them that are heteroscedastic, and it kind of averages it all out. And the cool thing about bootstrapping is it's a couple extra lines of code depending on how crazy it gets, but it's one of the only ways to do bootstrapping that you don't have to pay $1 zillion. So the bootstrapping function SPSS is another like $3 or $4 grand. So while it's annoying to do in R because you have to look up all the code for it, it's at least free, right? All right. So after all that data screening, now into the actual regression. So did it work? And of course it did, because otherwise this would be a boring lecture. Although I don't know if I can beat how crazy this has been today. So do a summary, and then look at the bottom part here. So it doesn't really give it to you in the ANOVA format because it's not really an ANOVA. So it gives me multiple R squared, so here's R squared. And then it gives me F, so it's 2 and 258. So I wrote it down here at the bottom, 2 and 258. It's 54.77, right? My p-value is less than 0.01. So my overall model was significant. So I can predict depression scores with variables, but which one? So R squared is greater than 0. Great. The next thing I want to do is look at which predictor. So are they both significant? Is only one of them significant? I know they can't be suppressing each other because they're not correlated enough for that. So what's the important thing. And so this is in the same output. It's actually coefficients first and then model, but generally you want to look at the model first. So what this does, it gives me the estimate here. Estimate is a fancy phrase for B. So estimate is the slope. Unless you're talking about the intercept, that one's pretty clear. So this is the y-intercept. So the average depression score is 54. It gives me the pill total. So for every one increase in pill, depression goes down negative 0.37. Okay, so it's decreasing. So as meaning in life goes up, depression goes down, which makes sense. It gives me my t-value. T is B divided by standard error. Okay. And then P out here. So it's complete with stars. However, my alcohol score doesn't seem to predict. So it's 0.99. So it is not related to depression scores. So meaning was significant. I've got B. T, where did that 258 come from? 258 came from here. 258 degrees of freedom. So it should match the second one for F. Okay, so whatever you write here for DF residual, or error, is the number that goes here for T. So I've got my slope, my t-value, and my p-value for all both of them. The only thing I'm missing is effect size. Okay, we'll talk about how to get that in a second. Okay, so it's kind of two steps. Is the model significant? Which predictors are significant? You can have predictors and be significant and the model not be. Okay, and that usually means you have too many variables. So if you have one predictor that's important and all the rest of them aren't, sometimes your overall model is not significant because of power. That's actually pretty common. So, two concerns now that I have this output. What if I wanted beta? Both of these scales are very different. So if I wanted to compare them to each other, I need to switch to beta. And then what if I wanted an effect size? Okay, so let's do beta first. We'll need this package called quantpsych. So you'll want to install that. That's not one we've used before. And then the function, thankfully, is lm.beta. Yay! So quantpsych. So it's lm.beta, and it shows you the two beta scores. Okay, we'll get that installed. Quantpsych is actually a really cool package. It does mediation and moderation simple models fairly easily for you. So I have a note at the end, like if you ever get to this point and need to do them, use this package. Right, so in standard deviation units, pill is 0.55, and the audit score is still really terrible. So I would still say that this one is better. Obviously, one of them is significant, one of them is not, but if they were both significant, this is how I could compare which one was better. Beta scores can get over 1. Write that down somewhere in your brain. Because people think about beta as R, and R can't get over 1. But beta is z-score, so it can be over 1. It can be 2.4. That would be a very large beta value. But they can get over 1. I get that email from somebody at least once a year. My beta is 2.5. I'm like, cool. They're like, that's not wrong? I'm like, So B, beta, and R are all the same variable if you have one x. If you have multiple x's, it's still z, so it can get over 1. It's not that common. That's why when people see it, they think they've done something wrong. All right, So, yeah, I'm sorry. I do want to do this first. Everybody's favorite Venn diagrams. I'm going to go back to talking about R, SR, and P bar for a second. So we have DV here. I've got two IVs. I have these labeled on here. A, B, C. Right. Yes. So a multiple correlation, or R squared, if you square it, is the overlap in all of Y. So it's A, B, C over everything. Okay. So this is model. This is all the variance. Because remember, the formula for R squared is is model variance over total. So it's the variance that overlaps between your predictors and your DB divided by the total. And then last week we sort of talked about SR. I said it's kind of hard to explain, so let me try and give it to you in math format now. So this is our SR is only the unique variance over the total. So that stays the same. It's the unique contribution of one IV all over total. So we did A here. So B gets taken out. B does not get taken out of Y. It only gets taken out of X. So we talked about SR last week. It was like the correlation between 1 and 2, given that 2 and 3 are correlated, but not that 3 and 1 are correlated. So B gets dropped out of the correlation between 2 and 3, but not out of 1 and 3. So you're only losing B from the numerator. Okay, so something distinct here. This is all IVs. This is one IV. So we're losing the overlap in B. So this is why you can't have variables, IVs, that are very highly correlated. If B was a huge section, the IV wouldn't look very important because you're going to lose B as part of the calculation. So the way to think about it is the increase of variance in Y when X is added. Now PR, we're going to keep this same idea. So it's only A. But now it's only over error. And not total. So SR is the amount that we're adding given X to the total variance. Right. So whereas PR is the amount that we're adding to the error variance. So PR squared and partial eta are very similar. Okay. So we have regular eta, how much variance total is there, how much model variance over the total. Partial eta is how much variance for that variable over error. Right? Same idea. Not quite the same math, but same idea. So it's going to be now A over the leftover variance, the residual. Because the denominators are different, PR is always larger than SR. Because it's the same numerator. And so this is always going to have a larger denominator. So PR is always larger than SR. Okay. So it's a proportion of variance X explains in Y, ignoring all other variables. So it takes out both B and C. Whereas before we had just lost B. Yeah, hopefully that helps a little bit. SR and PR. So most people report PR because it's bigger. And it's kind of like a partial eta. So the way that you're going to get PR is to use our P-core function that we did last week. But you have to remember to square it. So it should be PR squared. So what I did in the code here, I didn't install this one. Type there. Is I saved them. So I've got partials equals P-core for my data set. And when you do that, it allows you to break down, you got estimate, statistic, and p-value, something like that. Now I can just take the estimate and square it. Maybe. Did y'all freak out? Oh, cool. Glad it was just me then. It should look like this. Right? So what you want to do is you want to look at CSD only. So just look at the DB. So I want to know the partial correlation with my IV to my DB. So for pill total, it's 0.29. For audit, it's just ridiculous. So pill is adding 29% of the unique variance. so to the equation, whereas odd is doing crap nothing. All right. Yay, I crashed R. It's everybody's favorite time of the day. Here we go. Let me see if I can get this to load. Yep. So you would report PR squared. Yeah, blah, blah, blah. Look at all the graphs. There we go. Okay. Oh, I turned off scientific notation when I did mine. There we go. Okay. So 29% is rather large. You still use the same rules, 0.01, 0.06, 0.14. Okay. So it's a large, unique variance added. And then on here, I put just how that would look. So I've got B, B or beta, pick one, pick your favorite, T, P, and PR. Okay. If you are working on an analysis that has a lot of predictors, throw them in a table, much easier. A big table, B, T, P, PR. Because that can get unwieldy when you have like 10 predictors. Or in the case of one study that we had where we had like 5 or 6 regressions and they each had 10, it was a huge table. It was frightening. The font was like 0.4 to make it all fit. Okay, questions on that stuff? Yes, no, not yet. I'll switch to hierarchical regression. We won't do data screening again, but also going to do dummy coding. God bless R because dummy coding in every other program sucks. And it's all, I'm a dummy code for you, so you can't screw it up. Woo. Well, I guess you could, but it makes it harder.
About the stable?
Yeah, you can, but it is much harder than it is in SPSS. Okay, so the difference between a multiple regression and a hierarchical regression is steps. So hierarchical regression lets me, and that's a word I cannot say, hierarchical, that's like too many syllables, right? Is I'm going to separate out my regression into steps. Okay? So sometimes that's called blocks, same thing. But I get to make the decision, so I'm going to do these variables and then these variables. This works really well if you have dummy coded variables, so we're going to kind of do two things at once. You don't have to have a hierarchical regression with dummy variables. You can also do it as a multiple straight simultaneous. I just kind of putting these together to save time to do one example, but it's not that if I have dummy, I have to do hierarchical. I just am doing it that way for this example. Okay. Why are these slides so fancy? That wasn't on purpose. Okay. So, this is a really good thing to do if you're doing theory testing. So I can look at how much I'm adding to the equation for this set of variables. So I can say, I want to control for this and then look at this. Okay. The bad part about hierarchical is that you're supposed to know what you're doing. I still don't think I know what I'm doing, really, so you're going to have a theory, at least. Okay. So you should have a theory on why this, then that. Okay. That's usually pretty easy if you're using this as control. Right, so I'm going to control for this and then do these other variables. That makes sense to people. The other thing is this is very similar to ANCOVA. So ANCOVA is like half hierarchical regression, half ANOVA. It's the hybrid cousin of the two. So if I want to answer questions, is my overall model significant? Model 1. Is the next model significantly different than model 1? So is the next step significant? And then are the predictors significant? So we just have one new question. Right? So is model 1 significant? Is model 2 better than model 1? Is model 3 better than model 2 if you keep going? And then are the individual's predictors useful? Usually used when you want to control for something. So in this example, we're going to control for family history of suppression, and then test if the different drugs are different. So I'm going to control for family history first. This is actually an ACOVA that we're doing. You could also do controlling for, what was I doing yesterday that I found out I was doing wrong this morning? Controlling for word length. What then predicts reaction times or response times? Turns out nothing because I was using the wrong DV. It also is useful when you want to do sets. So sets are when you have a bunch of variables that you want to treat as one. You don't really want to average them, and maybe one of them is good and the other ones aren't. Sets are really helpful if you have correlated variables. So God bless my friends that I work with, but they always want to use like 3 of these meaning variables, and they are correlated between 0.7 and 0.8, and I cannot convince them that this is not a good idea, because that's 50% of the variance that overlaps. So they cancel each other out. So we do things as sets instead. So the set of meaning variables, all of them together is significant, but no individual one is, because they're messing each other up. It also is helpful with categorical variables to treat them as a set. So altogether, this variable adds x. Individually, here are the differences. Okay, and you'll see this in a minute. Hopefully. So categorical predictors. If they have 2 categories, men and women, there's like nothing to do. It will just run the predictor, and it'll just be like a correlation with 2 predictors. Right? So it's the difference between mean 1 and mean 2. So let me show you. If I have my men and my women, and I know men is coded as the lower group because it's alphabetical order, right? And I get a B value is 1.2. What it's saying is that as I go from men to women, the increase is 1.2. So B is the mean difference between men and women. If you aren't sure, run the means. Subtract them, you'll see it's B. And we'll do that in a second. If I have 3 categories, though, I can't really treat this as... Okay, it's not a good example anymore. What do I have? I have no treatment. Paxil. Cheer up group. Just tell people to cheer up. I can't treat that as continuous because it's not. So I can't just like keep plotting them on X here. So instead I have to do something else. Okay, that's called dummy coding. So dummy coding is where it takes each one of the categories and creates a pairwise combination. So my categories really are no treatment, it's Paxil, effects. I can't remember. Hold on. I have them written down. H data, $, treatment type. There we go. Placebo. Paxil, Effexor, and this goofy cheer up example. So I have 5 levels. What dummy coding does is it creates you pairwise combinations. And we won't get into the crazy like coding scheme that it actually does because you don't have to do it. So whatever group is first, it treats as the control group. So that means like whichever one pops up first here. So remember, if you need to reorder them, we can use the factor command to put this one first. And you can also use relevel, but we've already learned factors, so let's stick with that. And what it does is it creates 4 new variables. So those 4 variables, which you'll see in the output here in a second, is the comparison of no treatment to Paxil, no treatment to effect, to placebo, and to cheer up. So dummy coding forces it to be pairwise. So when we did ANOVA, we did post hoc tests that were pairwise. Right? In regression, it forces them to be pairwise, but picks one as the control. So if you wanted every single possible pairwise comparison, so if I wanted to know Paxil versus Effexor, you have to re-level it and run it again. Okay, so you would basically rotate this and make Paxil the control group, and then rotate it again. So my proof that ANOVA and regression are the same thing. It's going to give me the overall model. That would be the same as my F omnibus test. And then it's going to give me all the pairwise combinations, which would be the same as running part of Bonferroni or Tukey or t-test. It doesn't give me all pairwise combinations because then it would freak out. That's a long story. But if you want, let's say, Paxil to everything else, you would re-level it and run the analysis again. All right. So what we're going to do is first control for a family history of depression, and then talk about the treatment. So I'm going to control for their sort of genetic background. Okay. And then let's see how much their rating is changed after treatment. Okay. So our first model is going to be after treatment is predicted by family history only. And then our second model is treatment is, afterwards is predicted by family plus treatment. And so the whole thing should be bold. But when you program the first model, you have to carry over the variables to the second model or it won't control for them. Then you're testing two very different things. Okay, so you're going to test this one and then add the predictors in. So it's like this one plus this one. So model 2 is like, here's more predictors, what happened? Don't take them out. Okay. Or you're not testing what you think you're testing. So let us try that. So you want to load the data set, which is around 95. And yeah, I just wrote my note, don't forget to data screen. And let's do model 1. Show me the summary. There it goes. So what I would do, I wrote it at the bottom, good, is I would say model 1 is significant. So here's my F statistic for model 1. So I got 1 and 48 is 0.005, it's 15% of the variance. Family history is a significant predictor. So B is 0.15, 2.92. P and R are the same. Because it's one predictor. So don't forget, all the correlations are the same. So I could have run PR squared. Actually, if I tried to run PR squared, it would have freaked out. Why? Because there's two variables. Okay. So there's no partialing to be done. So when you have one predictor, you can PR and R are the same. Now let's try model 2. So I see let's run model 2 first. JK. So now I've added treatment in here. So I'm going to run that. If I look at the overall model, I can tell it's still significant. Right? So my F statistic is 5 and 444. Why is it 5? Well, I have one family treatment variable and 4 of these control variables, these dummy-coded variables. Sorry. So that's where 5 is coming from. So if you're going to data screen with dummy-coded variables, you might try running the model with the dummy codes first if you aren't good at counting them. So this is what K is here. It's the number of predictors. And it's significant, but sometimes what will happen is the first model is significant and the second model doesn't add something to it, but the R squared is still large enough that it's bigger than 0. So let's say the first model R squared was 0.3 and the second model R squared is 0.31. Okay? 0.31 is still bigger than 0, but we've only added 0.01, and that's not really that helpful. So this overall model statistic is not useful. So what we're going to do is compare the two models with another function. This time we're going to use ANOVA that doesn't run ANOVA. Right? Before we talked about don't use the ANOVA function, it does something else. Use the something else. Okay. So the ANOVA function compares two different models. The AOV function runs ANOVA, but ANOVA function compares models. And so I'm showing that the addition of the treatment variable went above and beyond the family history variable. Okay. So is my change in R squared better than 0? Yeah, kind of. Basically, this is like if you're tipping at a restaurant and you give a nice tip and your friend's like, oh, well, they've already done enough, so I'm just going to give them 3 cents. This is testing that everyone has added something significantly to the pot. Okay. So what we want to do is it's just ANOVA, so I got Model 1 and Model 2. This is why you have to run them separately and save them separately. And so I wrote that, I have it down here. And it is not the easiest code to read. So I did my little delta symbol. Delta means the change in F. So I got 4 from here under DF, and then 44 under res DF. Why are they in that order? I don't know. Okay, so it's 4 and 44. And then that equals F, so F is here under F. Here's the change in P, so 0.002. And then my change in R squared, I just did some math. Okay. So, and I pulled out my calculator because I'm not that good at math. Okay. For Model 1, R squared is 0.15. For Model 2, R squared is 0.42. Math, 0.27. Okay. So 0.42 minus 0.15. So I did not pull that out of thin air, I just subtracted them. So what that tells me is the addition of the set, all 4 variables, is significant. And that really lets me treat treatment as one variable. So treatment is an effective predictor. Now which treatment is better is the coefficients part. So anytime you have dummy coded variables, it helps if you treat them as a set, because then I can tell if that whole variable is significant and then break it down. Otherwise, you're going to be looking at them as like 4 different variables. So overall it's significant. Now what is important? All right, so this is my reminder of what's going on. So it compares the control group to a coded group. So negative numbers mean that the coded group is lower. Positive numbers mean that the coded group, wait, that says the same thing, doesn't it? Yeah, it does. You know what it should say? That's what it should say. Just use tapply to figure out what's going on. Because that said the same thing twice. Right? So it's a control group to a coded group, run the means, and B is the difference in the means. Okay. So let me see. If you look here, you should have all the variables. I put it in PowerPoint to make it bigger. Ignore family history. So one thing, this is totally not consistent across everything, is only look at the variables in the step that they're entered. So family history was entered in Model 1. I talked about it already. Moving on. Some people don't agree with that. They say you should talk about it twice. And I'm like, I've already talked about it once. I don't want to talk about it anymore. It's over, right? So I'm only going to look at these 4, but that's inconsistent across research labs. All right, so what is it doing? First one is treatment, the no treatment to placebo, then no treatment to Paxil, to Vexor, to cheer up. So at least it tells you which one is which is nice. And then I wrote out what that meant down here because I ran tapply. But note that this is not all pairwise. If I wanted to compare cheer up to my Paxil group, I would have to re-level it. Put the cheer up group as the first one. So make them first in line. Sorry. So how did I figure out which ones were which? I'm not good at this either. So I ran tapply and I just looked at it. Okay. So my no treatment group has the highest mean. And remember, this is depression rating, so high is bad. My placebo group has a lower mean. And so that's why the placebo group has a negative score. So it's 15.8 minus 11.7, and that's where this number comes from. Okay. My Paxil group has a lower score, but it's not significant. Here. My Vexor group, is that right? Is significant. That's interesting. Right? Because it doesn't look that much lower. Maybe I have these backwards. Anyway, my cheer up group is significantly lower. Okay. So that is strange. Anyway, so that's why I tell you to figure out what's going on, is to run T of Y. Oh, that's because this is the difference in means controlling for all the other ones. I was like, why doesn't that math look right? So it's not perfect because it's the difference in means between the two groups controlling for the fact that there are other groups in the model. Okay. So that's, but looking at the means will help you figure out which way it is, up or down. That's why this one is significant, but Paxil is not. All right, where am I at? So how do I get PR squared? Since the data is not actually coded in that format, and if you try to run PCore on a categorical or factored variable, it just goes bleh. What you can do is a little bit of math. Okay. So it's t squared divided by t squared plus df residual. Sorry, I forgot to add that. Df residual. Okay. Or you could just do Cohen's d, since they're mean comparisons. Equally likely, I think, in the literature. So what I did down here was I just filled in t for one of them. So let me look at my summary again. So I pulled t 4.052. I don't know where the heck I got that from. Oh, t, sorry, here. So t from my cheer up group on degrees of freedom residual is 44. And then that means that the PR squared for that comparison is 0.27. And you would have to do that for each comparison, one at a time. Or you could calculate Cohen's d. And this would be an independent t-test because they're different groups of people in the treatments. Okay, so last but not least, things that we don't have time to cover, rats. So mediation, because I think Mitchell will talk about these a little bit next semester, so just kind of give you like a preview. Mediation is understanding the relationship between X and Y with a third person in the room. So I always think about mediation as the third wheel analysis. Okay. It's helping you understand third variable problem. So if I have X and Y, if I add the mediator, does X and Y change? This is like you and your friend hanging out, whatever. Your other friend comes over, and then you and your first friend have a different conversation. Okay, so the relationship changes because of N. Moderation is interactions. Okay, so understanding that different levels of X's predict Y. Okay, so there's an interaction between your two variables predicting Y. People get these confused. It is easy to do, and will say that they're doing moderation and do mediation, and they're reversed. So if it says interaction, it's moderation. If it's talking about the third variable, it's mediation. QuantSci package does both in a pretty simple way, believe it or not. Huzzah. Because coding moderation by hand was like, do I have time to cover that? Oh, hell no. So that's what mediation and moderation are. Like I said, if you're interested in them, and then you get to the point where you're like, oh no, my thesis, I need to do this, let me know. Because by the end of next semester, I'll have a video for those. Right now, it's all panic.